In this video we're going to look at the second part of the erosion and sediment control process, and that is sediment control. In the first video we looked at erosion control, which is preventing erosion, but even with the best will in the world you are not going to stop erosion from happening. You're just trying to minimize it. So that leads us to the second step, which is sediment control. What are you going to do with the sediment that's been produced? You recall that sediment is the soil particles that have been dislodged by rain or wind, and which can flow into the natural water system. If they get into the natural water system, they're going to cause problems with the ecosystems and the plant and fish life that are in those systems, and then it's going to flow onto the receiving water bodies, the estuaries and streams and stuff, estuaries and oceans, and that's going to cause problems there. So it's generally a bad thing. So once again, at sediment control, we're not going to pick up all of the sediment. We're trying to keep it down to a reasonable level. This is section F of GDO5. You recall that's on the Auckland Council website for those of you that aren't on Moodle, and it's a really good document. So let's look at sediment control. Basically, it is, what do you do with that runoff which has sediment in it? And you can see that there's all sorts of things, and we're going to look at a few of those in this video. So the first thing that you need to do is you need to pick up the sediment laden runoff. So at the bottom of your site, along the bottom, you will have a dirty water diversion channel. Now remember, we talked about the clean water diversion channels for erosion control. They're at the top of the site. Down the bottom of the site there's the dirty water diversion channels, which is picking up that sediment laden runoff and transferring it to a treatment device, which we'll look at in a minute. And it's just basically a drain. And the best way to cut a drain is to excavate there and then bund it there and then roll it. So you can see that there's the existing ground level, and what they've done is they've excavated out this, and they've taken the excavated material and built a little bund there, and they've rolled it. You need to make sure it's stable, because you do not want this thing sort of breaching. And then it flows into a sediment pond, a sediment retention pond. These are quite complicated devices. They don't look it, but they are. So what they are is the water flows in there, so you can see that there's the dirty water diversion drain there, I think it is, and then it's flowing into this bit here, which is the forebay. So the forebay is designed for easy access, so you can see you can sort of drive an excavator up here, you could drive trucks up, and so the forebay is picking up most of the sediment. So most of the heavy sediment will actually get into the forebay and it'll drop out there. So it's the first level of treatment, and then it flows over the this bund here. So you can see at present there's not much rain, so it's just sitting there. It's not going anywhere, it's just sitting there, and that increases the amount of sediment that's dropping out. But when the rain comes in, it'll rise up and it'll go over top of this. This needs to be level, and it needs to allow sheet flow into the second part here, which tidies it up a bit more. So as the water flows along here, usually 3-4 days, the sediment that is left in the water will actually start dropping out as it moves along there. Normally the proportions are 3 to 1. That is to encourage plug flow. If it was any thinner, it would be going too fast, and it would be resuspending the sediment that settle on the bottom. If it was any wider, then you'd end up not being able to distribute the flow across the whole width of the wetland, and there'd be short circuiting. There'd be little channels sort of forming. So we've found that sort of a length of 3, a proportion of length of 3 to 1 wide is about right. This one's maybe a little bit narrow. And you can see at the end there's the outlet structure, and we're not really looking at it. You need to look at GDO5 for that, but you can see that there's a T there. And so what that is, there's an outlet there, and that floats on the surface. So you can see that's just floating on the surface there. So it's two pipes. The top pipe is sealed and is afloat, and the bottom pipe is the outlet. It's got holes in it. So the float means that, and the T can go up and down, so that can go up and down as the water level goes up and down. So you're always taking the water off the top of the water column. So you're not picking up the stuff at the bottom which might have sediment in it. You're picking up the water at the top, which is likely to be cleaner. So it's taking that clean water off the top, then it flows into this manhole there, then from the manhole it flows into the natural water system. Notice the manhole's got an open lid there, so if the T-bars get beaten, that there's too much flow going in, rather than sort of flowing over the bank there, it will go into the manhole. It will short circuit the system, but that's better than having the flow going across there. Now if that gets beaten, it's going to flow over this geotextile here into the natural water course. What you do not want is the water table to get up high, the water level to get up high enough so that it goes over top of these. If it does that, then it's going to erode the bund out and the whole silt pond is going to fail. It's all going to flow out through that, causing more sediment in the stream than would have happened otherwise. So you've got levels of protection there. Ideally the water goes in, is taken off the top, it's decanted off the top by these. If they get beaten, it goes into the manhole off the top, so the top surface water goes into there. But if the whole thing gets beaten, then it flows over this diversion channel. Another thing to look at is when the water flows in, this is not from Auckland, I can tell that, is in Auckland we have very fine clays, and so we normally treat the incoming water. And I'll just show you that now. So in Auckland, our clay particles are negatively charged, which means they repel each other. They don't clump together very well. Now, when soil particles clump together, they are more likely to settle. It's easier to settle out them. If they're just a whole lot of small clay particles, they're going to stay suspended in the water column for much longer. So if you can get the soil particles to clump together, then they're going to settle out quicker, and therefore the silt pond, the silt pond is going to be much more effective at removing the sediment. And so the way we do it in Auckland is oftentimes you don't have power or anything like that, so this is totally doesn't require power at all. So there's a little shack there, and water fluid falls on the roof, and then it flows into this header tank here. The header tank then sort of flows into this displacement tank, which sort of, as it fills up, sort of drops down and feeds flocculant. So this is where the flocculant is, and it flows into a hose which overflows into the incoming water. So this thing only works when it rains. So when it doesn't rain, flocculant is not getting fed into the water. It's the rain that causes the flocculant to get fed into the water. What the flocculant that we normally use in Auckland is called alum, polyaluminium chloride, or PAC. And what that does is it neutralizes the negative electric charges between the particles. So it causes the large flocks to attract together. There are also coagulants. A coagulant will neutralize the negatively charged particles, which causes them to attract together. A flocculant attracts them all together to form a big clump. All you need to know about this is that they cause them to form bigger chunks of soil, which will settle out quicker than they would have otherwise. And in Auckland, you have to have these because of the soils. Other areas, the soils might be coarser, they might be sands, they might be silts, and they'll settle out just fine. Decanting earth bund. For a silt pond's really required when you get over 3,000 square meters. So for a smaller job like a house lot or something like that, you'll have this decanting earth bund, and it's just like a little silt pond there. So you can see it's got the little T connection there, it's got a little pond there, and so what happens is the water flows in, ponds in there, and then decants out off the top there. So that's for smaller sites, less than 3,000 square meters, or 0.3 of a hectare. Another protection device is a silt fence, which is basically just a geotextile fence. So that's geotextile. Geotextile will let water through, but it will not let silt through. So the water flows along, and it acts like a bit of a filter. So it acts like a filter. The water will flow through, and the silt will be trapped on the fence. Now these things are okay for small flows, but a concentrated flow will bowl the thing over and will actually push the sediment through the mesh, if you like. So the idea of it is to have it over a long period, a long expanse, and there's a sheet flow going across the site here, and it will pick up that sheet flow. So lower velocities, it'll also reduce the velocities down to prevent erosion. Oftentimes you'll put the sediment fence in first. So if you say have an area, you'd put the sediment fence in, and then you'd build the silt pond, because the silt pond is an earthworks activity. So oftentimes you'll put the silt fence in as an initial protection, and then build the other protections on the other side of it. It's also useful for isolated areas where you can't fit in a dirty water diversion channel or a silt pond. So here's a detail of it. So you can see it's a waratah, which is like a steel post driven into the ground. The silt fence is carried on into the ground, so you can see that it forms, so it doesn't allow the water to undermine it, to go underneath. And it usually has wires along it to tension it up, to make sure that it's not going to sag under the water force. Another method of protecting of collecting sediment is filter socks or silt socks, and basically they're straw or some other material in a geotextile, and they sort of form this sock sort of thing. So inside of that there's straw or some sort of filter material, so the water can flow into there. It gets filtered by the geotextile material and the straw, and then clean water hopefully goes into this drain. So here they put a filter sock, a silt sock, around a drain, so that drain leads to a natural water course, so you need to protect that. Here they're actually protecting the road, so they're preventing all the water flow from here contaminating this road, because this road probably flows down to a natural water system. Over time these things can be left in place, and you can see that they've established grass in between the filter sock here, so they've used that as a retaining wall. The other thing to remember is inlet protection. On the previous slide we looked at using a filter sock for inlet protection. Here they're using a geotextile covered in aggregate. The stormwater system flows into the natural water system, so you have to protect that as well. So you need to look at the prevent dirty water getting into the stormwater system, as well as flowing directly into the natural water system. So you can see that there's a whole lot of things that you can do to capture that sediment, keep it on site, but still allow the water to flow off site. And once again, it's not an either or. You put as many layers of protection in as you can. So you might have a silt fence, and then a sediment pond right next to it. Okay, so you oftentimes will have several layers of protection, just to make sure that you're providing as much protection as you can. However, it should be noted that these things are not 100% efficient, and some silt will still get through into the natural water course, and that is a problem, and it needs to be considered. That does need to be considered when you're designing the system.